Now, with that said, I want to share with you a couple of additional things that Hypothesis allows us to do. Hypothesis is a very sophisticated tool, but ultimately there's really only a couple of parts of it that we really need to use in our regular practice. When we're setting up a test, we can set up the parameters of the different strategies that we have. And we have more strategies than just integers and floats. We can also do lists of things. We can do dictionaries of things. We can also do, I think this is written, dictionaries. We can also do iterables of things where they may not even be concrete iterables. There's also another one that I use fairly frequently, builds, where builds allows you to pass in a Python function with some keyword arguments that will pass into that. And I often use that if, for example, I want to write a test that operates on a sequence of items, but I don't really care what it's a sequence of. So I might say something like, these are iterables of builds object. So the thing that I'm testing here doesn't have any other assumptions about what it does. Here I might say assert sorted x's equals sorted x's. We'll assume that we can sort this in a stable fashion. And here we'll say. And there we go. So we can, oh, and this, ooh, that's interesting. That test failed. Very interesting. So this test, oh, because it's an iterable. See, I didn't consider that. It's an iterable. We exhausted the iterable. This should have been lists or something concrete. You see, it's often the case that when we put these tests together, we even discover, oh, I thought it was going to be this way, and it was going to be the other way. And I feel like that is really the best we can possibly get out of this testing activity. That is a very positive outcome where, again, I'm not paid, I'm not compensated to write tests, but definitely if they're telling me things that I don't know about my code, that is very valuable to me. Well, other than these other strategies, we can do some filtering on these tests. Remember, we have a particular test budget, and we want to make sure that we can filter down to interesting properties of the inputs that reveal properties of the outputs. And these parameters that we have may not be sufficient for us to constrain ourselves down to what we actually expect that this test will work with. So we can take the integers and we can filter out of that selections that we have. I find this is necessary when, for example, we have functions that take very complex inputs, which maybe even have interdependencies between them. For example, if it's the case that we have, well, actually here, this would be something where I would, for example, randomly generate some input data and then filter it down to the ones that I could then use to construct something else. So I might say, we build something in some fashion using some create method or some, from params with the parameters being pulled from some distribution of some nature or another. In addition to controlling how we generate those assumptions, those given inputs, we can also record information about our tests. Because remember, if we set up the partitions and we say, look, we're going to let Hypothesis try and discover a representative value with a certain budget in those partitions, well, it's definitely the case that we may want to have some statistics about how we tested this. And so we may be able to annotate our test with some information about what we tested. And so here you can see during our test, we tried 100 examples, of which 50 were odd and 50% were even. It's the case that these kind of statistics may be very helpful because when we discover that we've missed something, we might want to discover why we've missed something. We might want to look at the statistics of what we actually did check. And we might say, oh, we only checked 1% under this particular criteria that matches to why the error occurred. Maybe we need to do some additional filtering or we need to give some additional guidance to how we proceed through that test space, how we discover all the inputs that we have. Additionally, Hypothesis allows us to constrain the tests in other ways. It may be the case that we have constraints on the inputs that are not individual to the inputs. Like, for example, we can say that this, it allows NaN values, and this allows NaN values, or these both don't allow NaN values. But what if it's the case that in our test, we expect one of these to be non-NaN, and the other one can be a NaN, that's fine. Well, we can't really encode that in this particular fashion, but we can provide some additional supplementary information to Hypothesis, an assumption. When Hypothesis sees this assumption and sees that this assumption has failed, it will not count the generation of that test against our test budget. So it'll say, okay, no, that's not what you're looking for. Let me go find something else. Additionally, we can even give Hypothesis a metric that we're going to try to maximize through other means. It's not through assume, but we can actually give it metrics and tell hypothesis, try to maximize this metric here to generate the best possible test. So we can give it even more direction for how to generate good tests. Additionally, it may be the case that we just want to note something when we do these tests. We might want to document something that isn't visible in the Pytest assert output. We want to just add some indication, the ID of the object was, and we can use that when we're tracking this down in our logs. We can add a lot of additional debugging that will only be generated in the case of a failing test, as opposed to when we typically do this with logging, where we just spam that log with a bunch of stuff that was completely okay, and then one or two messages that were wrong, and we're trying to figure out, okay, which test failed, which is the wrong message, what's going on? Here you can see hypothesis makes this very, very easy. Furthermore, it may be the case that certain tests that we want to write are actually pretty patterned. Hypothesis can even automatically generate these tests for us. Now, it can do quite a bit of automatic generation for us. It can even automatically generate what the given parameters are. I think that's maybe not that useful, in part because I put an annotation, say this is an incident. That's not that much harder than saying given x is in it from integers, y is from integers. That doesn't seem to be that difficult. But I can see where the general approach of ghostwriting tests might be valuable, because if we go back to something like our bubble sort, we can think the bubble sort should be idempotent. The bubble sort should be equivalent to the sorted built-in. And rather than having to write test bubble sort with my input, and I have to do a given, and I have to indicate what that input's going to be, like that, and then say, okay, first equals the bubble sort on my input, and then again equals the bubble sort, we'll call this output actually, on this output, and then assert that these are equal. I could just mark this as, or I could just automatically generate a test for idempotence. Similarly, I could generate a test for equivalence. And I think that's moderately useful. Although, in truth, I do think that it'll be pretty quick for you in a lot of tests for you to say, you know what, I actually just have to write this out, because I might not need to check for exact equality. I might need to check for something like all close, because for whatever reason, maybe there's some other noise that I anticipate seeing in this test. And of course, these two don't give you the same level of fidelity of checking that. But still, for writing really simple, really fast tests, this is quite helpful. Now, I want to spend the remainder of our time taking a look at some tests that I actually wrote and some tests that I actually shared with you in a previous session. If you remember, we recently went into the itertools module and we rewrote everything in the itertools module. And we rewrote this as the first step of building what we might want to call a corotools module, a version of the itertools module that works with pumped generator coroutines. And so we went into the itertools module and we rewrote everything that was contained within, handling as many of the different keyword arguments, getting as close as possible to an exact working copy, or an exact copy, that is. We even rewrote certain parts of the Python built-ins like enumerate, map, and filter, and zip as well, just to make sure that if we use those in order to implement something else, we were using our own personal versions of these to really make that a complete example. How do we know if this code actually works? Well, we do have an exact equivalent, so we could genuinely check each one of these against an oracle that's provided to us by the existing implementation in the itertools module. And largely, that's what we can do. We can say here, take some input for enumerate, take some starting point, and make sure that all the values are equal for the built-in enumerate and for our own enumerate. We can do the same thing for something like mapping or something like filtering, for a zip, for accumulate, and so forth and so on. But I think we can supplement these tests with something a little bit better. Now, obviously, it's the case that we're probably assuming that the itertools module itself already has enough tests, and so maybe there's not that much that we're adding. But as an example, if we were to assume that we were doing this from scratch and that we didn't have these oracles, we might think, how do we actually go about writing a test here for these things that doesn't presume that we know the output, that doesn't presume that we have easy availability of that oracle. And so let's see if we can work through some of these examples. How do we test enumerate without knowing what enumerate does? Well, we know that the definition of enumerate is we get something back that is a tuple of two elements. And so a very, very naive test would be, let's test our enumerate, and let's make sure that's our enumerate. Yep. Let's test our enumerate with just something simple like this, and let's just test the length is equal to 3. This isn't a property test. This is a pretty dopey test, but you know what? If something catastrophically breaks, this test takes less than a microsecond to run. This is a very easy test and pretty good bang for my buck. In a very similar sense, I could say, let's test that if this thing returns, let's do a next on this. This thing will return at least one value. That next ensures that it returns one value, and that it'll return something with two elements. Maybe it's a tuple that it returns, maybe it's a list that it returns, but whatever the case is, there's two elements there. Now I've gotten some of these smoke tests out of the way. Now I can think about something a little bit deeper. I know for enumerate that it's supposed to return two things, and the second of those things should be identical to the thing that was passed in. So if I have, and here I'm going to write this as a separate test just so we can reuse some of these pieces. I might say, okay, let's assert that our enumerate called on our iterable with our starting point, and just for reasonability's sake, we'll slice this to the first 100 elements, like that. Well, what we know is that all of the values in this structure should match the original values of the iterable. Now here, since we have an iterable that's a list of integers, that's concrete, so that's pretty good. So we could zip the actual and the iterable. We could say if we zip these together, we get some structure that looks like this, and some value here, and we know that those not only should be equal, but they should be identical. It should be the exact same Python object. So there is our test enumerate. Now, note that this is a very good case where we could use our Pytest dependencies setup so that we test maybe this test first, or these dumb tests before we test the more sophisticated tests. But I think we get the general gist of how we might go about doing this. What else we might do to look at this is we might say, you know what? I don't know too much more about how enumerate works, but I know that the first value that I get back should be monotonically increasing. I know that it should be, each value should be larger than the other. And I know that the very first value should be start. I don't know that I care what the last value is, as long as it starts at that point and it's monotonically increasing. So again, I can say, let's take all of the values here for x, y in, well, n-wise, the actual. We'll grab just the initial value from that, like this, and we'll assert that x plus 1 equals y. Or, if we're not even certain that these are integers, or if we don't really care that these are integers, maybe they're floating point numbers, maybe that's within our scope, we could even just say that they are smaller than each other, they're strictly smaller, or we could even say that, if we want to be really loose, that they're about a value of 1 away from each other. All of these are acceptable, and it really comes down to what guarantees we want to communicate on our enumerate and what guarantees we want to really ensure are met every time we make changes to this code. Additionally, another simple one would be we could check the actual first value and just make sure that's equal to start. Now, if we look at these tests, not the two smoke tests, but the remainder of the tests, note, we have not used enumerate. We have only very slightly assumed that we have the behavior of enumerate maybe here. But for the most part, we've checked some of the guarantees. We know it starts at a certain point. We know it includes the original value. And these are pretty exhaustive tests. I can't think of a change that we would make to enumerate that wouldn't break these tests if that change happened to be genuinely wrong and affect our end users. And I don't know that I can think of a change that we'd make to enumerate that wouldn't affect our users, that wouldn't be caught by these tests. And so you can see it's actually a nice exercise for us to put this together. And of course, working on things like iteration helpers really helps us because they tend to expose the details that we can have properties on.